All right, today we're going to take a journey deep, deep inside the human eye. We're here to talk about glaucoma, which is the #1 cause of irreversible blindness in the world. We're going to see exactly how this silent disease works its damage, neuron by neuron.
So first off, let's just talk about the sheer scale of this problem. We're talking about over 70 million people around the globe who are affected by glaucoma. But here's the really scary part. It's not just the number. It's the fact that most of these people have absolutely no idea they have it.
And that's really the heart of the issue, isn't it? Glaucoma is often called the silent thief of sight for a reason. This review from JAMA points out that in some populations, as many as 90% of people with the disease don't even know it's there. It can quietly progress for years without a single symptom, which means by the time you notice something is wrong, the damage is already severe.
Okay, so to really get how glaucoma does so much damage so quietly, we need to first understand what it actually is. And you might be surprised to learn it's not quite what you think.
Okay, so look at the words on this slide. This is super important. You hear glaucoma and you immediately think eye pressure, right? But that's not the whole story. At its very core, glaucoma is a neurodegenerative disease. It's about the death of very specific nerve cells, these retinal ganglion cells. They're the literal data cables that connect what your eye sees to what your brain actually perceives as vision. Once those connections are gone, they're gone for good.
So, what kicks off this whole chain reaction? What causes these crucial nerve cells to start dying off? Well, in most cases, it all starts with what you could basically call a plumbing problem inside the eye. Let's take a look at how this pressure system is supposed to work.
Yeah, it's kind of like a basketball or a car tire. Your eye needs to have just the right amount of pressure inside it to hold its round shape and function correctly. We call this intraocular pressure, or IOP for short, and keeping that pressure in the sweet spot is a really delicate balancing act. The key player in this whole system is a fluid called the aqueous humor. The best way to think about this is to imagine your eye is like a little sink. You've got a faucet called the ciliary body that's constantly producing this clear fluid. And of course, you've got a drain to let the extra fluid out. When everything's working right, production equals drainage, and the pressure stays perfectly stable. Okay, so here's where the problem starts. See that drain? It's a spongy, filter-like tissue called the trabecular meshwork, and it's the critical piece of the puzzle. Over time, for reasons we're still figuring out, it just gets, well, clogged. It becomes less and less efficient. And this is the part that's so important to get. The faucet is still running at the same speed. The problem is the drain. And when the drain can't keep up, the fluid backs up and the pressure inside the eye slowly starts to climb. All right, so you've got this pressure building up inside the whole eye. So you have to ask, where's the weak spot? Because it turns out the damage isn't spread out evenly. Nope, the pressure finds the one single weakest link in the chain. You know, for all its amazing complexity, the eye has what you could call a design flaw, a structural weak point. And all of that rising pressure, it gets funneled right to that one spot. Yeah, all of that force gets concentrated at the very back of the eye, at the exact spot where all of those millions of delicate nerve fibers, the retinal ganglion cell axons, bundle together to become the optic nerve and punch their way out of the eyeball. And this weak spot has a name, the lamina cribrosa. The best way to picture it is like a microscopic sieve or a colander at the back of the eye. All those nerve fibers have to thread their way through the tiny holes in this mesh to get to the brain. And because it's full of holes, it's structurally the weakest part of the eye's tough outer wall. It's the first thing that's going to give when the pressure starts to build. So as that pressure builds, it starts to push on this sieve-like structure, causing it to bend and warp. And as it deforms, it physically pinches and squeezes the nerve fibers passing through it. This is the very first injury. It's like someone is physically squeezing the data cables that connect your eye to your brain.
But you know, this physical pinching is really just the start of the problem. It sets off this catastrophic chain reaction at a cellular level, turning a simple structural problem into a full-blown biological crisis.
You got to understand, each one of those nerve fibers is like a super busy two-way highway. You've got outbound traffic, called orthograde transport, which sends visual data to the brain. But just as important is the inbound traffic, or retrograde transport. This brings essential survival signals back from the brain. They're basically little messages that say, hey, you're still connected, you're doing a great job, keep on living. So when that lamina cribrosa gets pinched, it creates a total traffic jam right at the exit of the eye. It creates a complete bottleneck. Stuff can't get out, but critically, those life-saving signals from the brain, can't get in.
And the fallout from this traffic jam, it's absolutely catastrophic for the cell. Starved of those survival signals from the brain, the cell basically gets a message that it's been abandoned. So it does the only thing it can do. It starts a self-destruct program called apoptosis. The internal structure of the nerve falls apart and the cell begins to die. This is the point of no return.
So, okay, we've got all this drama happening at a microscopic level. Cells are dying, supply lines are cut, but how does that turn into something that a doctor and eventually a patient can actually see?
So when your eye doctor shines that bright light in your eye and looks at your optic nerve, this is exactly what they're looking for. A healthy nerve has a nice, full, pinkish rim of tissue. But as millions of these nerve fibers die off, that tissue literally vanishes. This creates a little depression in the middle of the nerve that they call a cup. And as more and more nerve fibers die, that cup gets bigger and deeper. They call this cupping, and it's a dead giveaway that damage is happening. And as you can see, that physical damage at the back of the eye translates directly to permanent blind spots out in your field of vision.
But here is the single most terrifying fact about glaucoma. Your brain is so incredibly good at patching things together and filling in the blanks that you can lose up to half of the nerve cells connecting your eye to your brain, and you might not even realize anything is wrong. The damage is profound long before it becomes obvious.
And all of this brings us to the big, crucial question. If the damage is microscopic, if you can't feel it, and you can't see it until it's way too late, how on earth are you supposed to see it coming? And really, there's only one answer. You have to find the damage before the vision is gone. And that is why understanding this silent process is so absolutely critical, and why getting regular, comprehensive eye exams is the only real defense we have.